Sure. First of all, let me congratulate to the conveners for conceptualizing and organizing such a critical event. Our glorious history of chemistry and related sciences validate India should definitely have a top position in modern science and technology as well. Thank you for inviting me here. And it's always enriching to hear Professor Ashutosh Sharma and Jayant. Without taking much time, I would like to introduce Professor Sharada Srinivasan. She is a professor at National Institute of Advanced Studies, Bengaluru. She received Padam Shri, the fourth highest civilian honor from the Government of India in 2019 for her tremendous work in archaeology. Professor Srinivasan's landmark contributions include archaeometric characterization of bronzes of South India using lead isotope analysis and archaeometallurgical studies on ancient mining and metallurgy in South India. She has worked on artifacts in the government museums across India and London. She is a fellow of the Royal Asiatic Society of Great Britain and World Academy of Art and Sciences. She has several prestigious awards and accolades on her name. It's hard to read all. So without taking much time with these words, I invite Professor Srinivasan for her lecture.
Thank you so much. Can you hear me?
Yes, loud and clear,
yeah.
Please.
Yeah. So it's very nice to be part of this very important meeting on chemistry in ancient India. And I thank Dr. Vivek for the invitation. And it's also wonderful to have, of course, that this meet is organized by so many important stakeholders, DST, the Royal Society of Chemistry, and TIFR, and so on. And thank you, Dr. Deeksha Gupta, for your kind introduction. And also it was great, of course, to hear all our speakers so far, and Professor Ashutosh Sharma and Dr. Jayant Sahasrabudhe and Professor Jagatap and so on. So I will, of course, concentrate more on the field and archaeological and
Professor Srinivasan,
yes.
sorry to disturb, but can you share your PowerPoint? It's not shared.
Yeah, I'm just about to try and do that. Where did yeah, that's right, share screen. Sorry. Yeah, okay. This one, right? So is it visible?
Yes, but can you do a slideshow, please? Yes, it's perfect now. Yeah.
Yeah. Okay. So well, I'll carry on without further ado, because I do see that you have a lot of speakers and so on, and this is a topic in which there's a lot that you know, could be talked about. So my topic today was going to be more of trying to focus a bit more on the zinc extraction and steel making evidence from the archaeometallurgical insights. And of course, this is a slide from Southern India and Agni Kundala, one of the polymetallic deposits. And as you can see, many of our old mines and so on have been extensively worked. And of course, while modern metallurgy has seen an exponential growth since the Industrial Revolution, several of the important innovations and inventions in chemistry and metallurgy and so on do have their seeds in ancient or traditional practices. And of course, metals were also extracted and utilized in stages progressing from those which are in the native state to those which could be more easily smelted from the ores, and those which were then more difficult to smelt. And of course, there are not that many when you compare the, you know, in a way exponential amount of metals and materials and simulated and synthetic and so on, other materials of the past, you know, the period following the Industrial Revolution. There are not that many in antiquity, but I would say that like all civilizations, India has also made some very significant contributions in terms of the early use of metallurgy and metals. And of course, copper was one of the metals is also found in the native state. And since we're talking about chemistry, one of the very, I mean, this topic of, you know, metals and materials also has a parallel in terms of the archaeological context, because we tend to describe these as archaeomaterials and archaeometallurgical studies and all that, which is looking at the history of the metallurgy or the history of material science and so on. And copper, of course, is one of the metals which is, although found in the native state, it also occurs as oxides and ores. And here you're looking at one of the mines in the Karnataka region, which is an open cast excavation with these green malachite stains and so on. And there is also a lot of the geochemistry and also the slag chemistry, which comes from the extraction process. You have the metallurgical aspect, but then there is also a lot of other kinds of inorganic chemistry and organic chemistry coming in there in terms of the understanding. And typically, you know, once the metal is extracted from the ore, in this case, these are malachites or copper carbonates, then it undergoes a smelting or reduction process. And typically what you do find in terms of the debris, you find these slag heaps in which the slag is the impurity which floats on top of the furnace, where all the siliceous impurities and the gangue and so on go into the slag, and then the metal, smelted metal, goes into the bottom of the furnace. But quite often the slag is very important really for us to study as archaeometallurgists and so on, because that, or even as, let's say, archaeochemist, I guess you could use that word more broadly, because the slag is what also traps some of the molten metal remains and so on. So you get an idea of what was being made and how it was being made. And this typically, for instance, near Ingeldal is you also find quite often the evidence of the ore crushing and the pestles and the mulakers and so on in pottery. In this case, some early historic pottery of the Shatavahana period, and there are also some carbon dates of the Shatavahana period of about the 1st, 2nd centuries AD. And of course, one thing I would say is that there has also been, I think, quite a lot of work from the archaeological community as well in terms of looking at the studies of metals and materials. We heard a lot about the textual sources, of course, but there has already been, I think, a considerable amount of work in also looking at the history of science and so on. So there's a need to put all of these together. So it's not that, there is really a void in that sense, but maybe there needs to be more of you know, kind of looking at the correlations and such like. And of course, you know, the archaeological or the archaeometallurgical record becomes more and more important in terms of, you know, piecing together many of these aspects, because in a way, text can be interpreted in so many different ways. But when you actually have the you know, material evidence, it becomes a different way of reconstructing the past using scientific techniques and so on, which are becoming more and more important in archaeology. So just to give you an example of, you know, the kinds of techniques and what can be done with looking at, you know, the study using modern spectrochemical analysis and modern scientific techniques and such like. So I had showed you some of the mining evidence from Ingeldal, and here you're looking at typically what we call slag. This is tap slag in this case, and this is what floats to the top of the furnace, and which is analyzed here. You look at the microstructure, and you can see that there is the copper metal in a way has segregated into these globules, is solidified from the molten state, and then it also has this sulfide ring around it, which suggests that this was probably sulfidic smelting. And you also have this glassy matrix around of the phalite slag. And now we also have, of course, these techniques. You know, it's gone from just optical microscopy to you can also do electron probe microanalysis, which has become also a very useful technique here, where you use wavelength dispersive spectroscopic analysis. And there is also this technique here where, you know, you can actually see the distribution of the elements and such like. In this case, this is an elemental distribution map for copper, iron, and sulfide. And you can see here very clearly how the copper is segregating into the the smelted metal, and then it has that sulfide ring around it. And then you also see this lathe-like phalite structure and such like. So, so that also tells us, gives us, various methods of reconstructing the traditional processes, or, the archaeological record and such like. And of course, copper, the various materials moved from the use of the Copper Age, the Bronze Age, and then the Iron Age, and so on. And I guess then even we could say today we are in the Silicon Age in some ways. And so it moved from those metals which could be smelted more easily to those which were more difficult to smelt. So I was going to concentrate in this talk on two remarkable stories. Partly also because they're very important in terms of the transfer of technology from east to west, from India to Europe. And they also represent aspects of semi-industrial scale of production, which were in some ways also forerunners of the Industrial Revolution. And of course, we've heard quite a bit already from Professor Jagatap on the zinc extraction, which I think simplifies my job a bit. So I may not have to dwell in so much detail in all of these aspects. But so I picked these two stories because they're really quite remarkable in terms of the implications as far as transfer of technology is concerned. And they deserve, a much more, let's say, prominent place in terms of even the way the metallurgy textbooks are written and the story of history of metallurgy is told. Well, when it comes to zinc extraction, of course, William Champion is the one who is really credited, or at least the patent for zinc production is with William Champion from Bristol in 1736 AD. But studies over the past decades by several scholars and archaeometallurgical studies and so on, and excavations and such like, have pointed out that it was really likely inspired by the Zawar process of zinc smelting, which I'll go into a bit more, and which has yielded the earliest firm evidence for the production of metallic zinc, which is really from India. And the production of metallic zinc was virtually unknown in Europe until William Champion established these commercial and industrial zinc smelting operations. And it was, in a way, also inspired by the Zawar process, which I'll point to. And of course, we all, and the International ASM Landmark Award was also given to Zawar in 1988 in recognition of the zinc smelting process. And of course, the Delhi iron pillar of the 4th century stands as a very, powerful testimony to ancient skills in metallurgy and such like. And there's a lot to say about it, but I won't really touch upon it too much, but mainly to point out that this is another of the industrial heritage, if you like, of India, which has also been accorded this ASM international designation as a historical landmark. And wood steel, which I will come to later, the crucible steel making tradition. Now, Benjamin Huntsman is credited with the production of crucible steel in 1740. However, as I will point out, the crucible processes were prevalent in India already for steel making, and it's thought likely now that he was inspired by the Indian wood steel crucible process. Now, the Aravalli ranges in Rajasthan are one of the most mineral-rich zones which were extensively quarried for building stones and also mined quite extensively since antiquity for copper, lead, silver, and zinc deposits and so on, because these are polymetallic deposits. And there is unique and extensive and evidence for semi-industrial production of metallic zinc in the Zawar area of Rajasthan in the region of Mewar near Udaipur. And I don't have time to go into too much of it, but I will point to some significant aspects. And as pointed out, these were mainly lead zinc ores and sphalerite and so on, which is found in the Dolomites in the Aravalli regions. And a lot of studies were also done since about the 80s by teams from the British Museum, the University of Baroda, the Peak Mining Museum, and Hindustan Zinc, which played an important role, along with Paul Craddock, KTM Hegde, and Lynn Willis, and so on. And subsequently, there have been quite a few excavations and studies. And there have been some radiocarbon dates, and which have ranged, I guess the most consistent of them range from about the 12th to the 18th century. And these have been from the ash from the furnaces for zinc smelting. Now, what you're looking at, and you see a lot of this in Zawar, is you actually see the retorts which were used for zinc smelting, which were used as building material more recently, because in a way, you know, the slag and everything, because of the phaelite and all, it becomes very impervious, so it can be used as a building material, and quite a lot of the walls and so on are made now of these kinds of retorts. And these are the remnants of the zinc smelting retorts. So basically an ingenious method was devised of the downward distillation of the zinc vapor. One should mention that zinc is actually a very difficult metal to extract in the metallic state, and that is partly because of the fact that once you smelt the zinc ore, it immediately sublimates, which means that it just goes directly from the solid state into the vapor state. So it doesn't actually, it's not very easy to get it in the liquid or the molten state. And which was one of the reasons why, in fact, it was so late in terms of the other metals which had been extracted more successfully before. And what was actually done here in Zawar, which was quite a distinctive process, was the distillation, whereby they used this downward distillation technique. And this was achieved by using specially designed furnaces and retorts with condensers and so on, so that it enabled the smelted zinc vapor to be very drastically cooled down to get a melt that could be solidified into zinc metal. And about 7 of these fired furnaces or koshtis were excavated in Zawar, along with numerous retorts which were found in situ, and these were intact after the firing process, and they would have contained the zinc ore charge. Now, what is also very interesting about the Zawar process is that this is one type of technology where there is a very good link with the textual evidence. For instance, the 13th, 14th century Sanskrit text, which has also been talked about, the Rasaratna Samuchaya by Vagbhatta, which describes this method of zinc production as Tiryak Patana Yantra, or the downward distillation. So basically, if you look at the schematic, you get an idea, but you can see here that there's 2 chambers over here, the top chamber where the retorts were actually fired, and the bottom chambers, and there is a huge thick perforated layer, terracotta layer in between, through which the condenser passes, so that there's a drastic cooling from this top chamber into the bottom chamber. And so basically the furnace is fired at about, let's say around 1000 degrees centigrade on the top. And here you can see this schematic of the furnace chamber. At the top you see the retorts, and then you see these perforated plates with the terracotta plates, and then the retorts going through. And at the bottom you would have had the stem of the condenser goes through that perforation down, and then once this cooling is achieved, drastic cooling of the zinc vapor, it gets condensed into the zinc metal, which could then be collected. And it's also interesting that, of course, the Tiryak Patana, or the downward distillation, that is already mentioned in the Rasaratna Samuchaya, but there are also other texts which mention various aspects of these technologies, such as the Rasendra Chudamani of the Chalukyan king Somadeva of the 12th or 13th century, where he mentions the Vrantaka Musa, which is basically a brinjal-shaped crucible. And it's a very apt description when you look at it, because it actually is a brinjal-shaped crucible. And then it has this hollow tube. And it talks also about the distillation of karpar. Of course, some of these terms, as in Sanskrit, it often happens, they're used sometimes quite variably. So one does need to actually understand the context before the translation is done. It was mentioned about karpur also is, of course, used to refer to camphor, but in this case, it refers to the zinc ore. And so you can see here, it recalls to the kind of retorts that you find in Zawar. And so it's a radical cooling from about 1100 degrees centigrade or so down to about 500 degrees. And then it solidifies to form these globules of zinc metal. And what you're actually looking at here at the bottom, you see some of the furnace remains, is also a Deccan zinc coin, which I was able to also study, which had a date of about the 4th century because it had this Deccan Brahmi inscription, and I'll come to it a bit more again in terms of the lead isotope analysis and such like. And this is perhaps one of the earliest, at least surviving examples of metallic zinc from the Indian subcontinent, perhaps one of the few from anywhere in the world as well. And what's also interesting is that it's like a droplet and the bottom is flat. So you can see that the distilled vapor has then condensed into this sort of globule, which is exactly as you would expect. So this is also another interesting aspect to it. Now, of course, the use of zinc or zinc ores has also been known in other contexts. For instance, Nagarjuna in the 4th century also mentions the rasaka, which may refer to the zinc ore or calamine, because calamine was also used for medicinal purposes, the zinc carbonate and so on. And it's also interesting, of course, that although zinc came into vogue much later, it's not to say that brass, the use of brass was not known earlier. Brass was used also in the Roman world and so on. And because as mentioned already, there is also the fact that you can actually make brass without isolating zinc, at least low zinc brass. So what happens, there was also a shloka mentioned, and that is also what I'm pointing to here, which is translated in Deshpande and mentioned in Craddock and so on, where roasting of calamine along with copper to give the gold, which is basically that you heat when you heat the zinc carbonate into the zinc oxide, and then it gets reduced to the vapor, and then the vapor gets into the copper. So it's called a cementation process. So this is what we call cementation brass. And the use of cementation brass was also known, for example, in the Roman world, where they called it aurichalcum and so on. But what was interesting is also that the cementation brass, there is a limit to the amount of zinc that can get into the brass because it is an alpha brass. So it doesn't have more than about 35% zinc in this type of brass. But what was interesting is that you do find a couple of samples from the Gandharan site of Takshashila, or Taxila as we call it, which is reported also by Marshall in 1951, which were reported to have over about 30% zinc. And so this is quite likely that they were actually using metallic zinc, because to get so much of zinc into brass, which goes past the alpha solid solution, implies that you had to have using metallic zinc. So as you see that zinc ingot over there, you would have had to alloy that to the metallic copper in this case. And of course, it's interesting, you know, for me as a dancer, this term rasa, which we keep hearing in the alchemical tradition, you know, this point was also made, I think it was by Ashutosh Sharma and Jayant and the others too, about the holistic and connected nature of Indian arts, of course, and sciences as we understand it. And, you know, the term rasa also keeps, you know, is very much a part of the Natya Shastra tradition and the performing arts tradition. And I think that, you know, there's probably an analogy, because even when you talk about rasa and the Natya Shastra, there is this connotation of a distilled essence. And so this is also, you know, the idea of distilling and so on. You also find that in this metallurgical context. And of course, there's, in Taxila, you do also have some distillation vats, which are of the Hellenistic period, which were used for alcohol. And so there's also a lot of this kind of tradition of, you know, general use of distillation processes. And of course, in the Vedic tradition, also the use of, you know, the soma and so on. So these kinds of knowledge systems all have fed into each other, so to speak. Now, I was talking about the alpha brass, and I just wanted to point to this image from the 16th century, from which is a Kerala Chera image of Vishnu, and it also has the eyes inlaid with ruby and so on. So this was found to be brass, and this is alpha brass, low zinc brass, so to speak. And the studies were done trying to use in situ metallography so that one didn't damage the image too much and so on. So I think, of course, an important aspect is to analyze a lot of our artifacts. And to that effect, a lot of my early studies have also been on the analysis of South Indian images. And the reason why I'd like to point to that is to some significance of some of the techniques that are used, particularly lead isotope analysis and spectrochemical analysis, for identifying some early artifacts of zinc, especially coming back to that coin ingot, and I think how I've been able to give it a more firm attribution using the lead isotope analysis technique. So this of course is a very spectacular Chola Nataraja bronze from Kankodu Vanittavam in the Government Museum, Chennai. And the analysis shows that it is a bronze of about 8% tin and 8% lead. And so this is actually leaded bronze. So a lot of these images were also of leaded bronze. And as you can see, there are still surviving traditions where the icon is being cast in the Tanjavur district. And of course, another interesting point which was also made by some earlier speaker is what you're looking at in the Zawar process, for instance, is the closed crucible process, really. And where it's a closed crucible which is fired at very high temperatures and so on. And here what you're seeing is, of course, an open casting technique and so on. So there were these various shades of looking at, the various traditions of casting and foundry techniques. So now I'll try and come, though I won't go too much into this, so you'll have to take my word for it in terms of the results. But what I wanted to point out was that this lead isotope ratio analysis was useful in terms of identifying some early examples of brass images, because now, as you know, that metal, unless it has, we do use a radiocarbon method of dating and so on, but that typically implies that the archaeological artifact needs to have some charcoal in it to be able to do this radiocarbon dating. And as pointed out with the Zawar furnaces, there were, oh, I've got 5 minutes, good God. So I haven't even managed to start on woods. I think I've got 2 separate talks here. Well, anyway, so this lead isotope ratio technique is one where basically if you have lead in an artifact, you can correlate the lead isotope ratios of the lead in the artifact to the ore source, because the isotopic ratios of different lead deposits vary in a very typical or characteristic way. So what I was able to do by analyzing various groups of South Indian images was to create a lead isotope profile for different periods of bronzes, for instance, Pallava and Vijayanagara and Chola and so on. So I don't want to go into that too much. And of course, if we had the lead isotope ratios of the ore sources, we could actually identify the source, which in this case was not easily possible. But what was interesting was that zinc ingot that I showed you also matched the lead isotope ratios for a 4th century Andhra oil lamp of the Krishna Delta, which was a brass artifact with 13% zinc, 8% lead, and 11% tin. And so that suggests that there was, apart from Zawar, because these ratios did not match Zawar, because Zawar falls in a completely different, when you do the plot of it, the PB 208 versus 206 is closer to 2.2 and so on. So this was not Zawar, but this is another early, seems to be another early mining source of, and for extraction of zinc, which seems to have been available in South India, though we don't quite know where that was. So there is, I guess, in that sense, all of these interesting leads, whether somewhere in the Deccan or elsewhere in India and so on. And this is also another early Andhra Lokiteshwara. Well, I think Bidri won't say much about it, except to say that there is also the metal used. The metallic zinc was also used to make Bidri ware in Bidar into the 14th century, inspired by the Muslim Bahmani sultans. And we did some analysis where it was found to be 90% zinc and 6% copper using XRF and such like. So I don't know how much time I have. I think I need another 5 minutes really, because at least 10 minutes, because this is quite an important topic. And these kinds of topics, you have so many interdisciplinary aspects to explain that you cannot really kind of just condense it. It's just not that easy. But I won't maybe go into it into too much detail really, but except to point out that Woods, which was a Europeanized version of the term ukku, was probably the first high-grade steel which was made in the world. And it was said to have been exported very widely to West Asia and so on to make patterned Damascus swords. And of course, these so-called Damascus swords, I'll explain how the pattern comes into it. And the novelty about boots, of course, was that it was an ultra high carbon steel, where we talked about wrought iron, which was used to make the Delhi iron pillar and so on. But ultra high carbon steel is typically a steel with a composition of about 1 to 1.5% carbon. As you can see in that phase diagram, you get an idea of where that lies. Whereas wrought iron has very low carbon, less than about 0.4% carbon. And you also have these records of the Arabs in the 12th century, such as Edrisi, who mentions the fame of the swords of Hinduani, which is represented as Indian steel. And so I had undertaken this microstructural analysis of a nail from Pattinam in Kerala in the 1st century. And that, so this is really the structure of typical hypereutectoid wood steel, which is this 1.5% carbon steel, where you have basically what has happened is that it has cooled from, this is, if you can imagine the 1.5% carbon steel, it has been heated to such a strong temperature that it has got, there's a sort of molten carburization where it has gone into the austenite phase. So it has, at least it is plastic, if not entirely molten, and that's how so much of carbon could get into it. And when it cools from that, you get this hexagonal matrix, which has the prior austenite, and then you have the pearlite inside it, and then the cementite grains and so on. So this structure of this nail from Pattinam very clearly shows that it is an ultra high carbon steel structure. Now, why that was really important is that when you forged it very extensively, you get this pattern of the alternating light cementite and the dark pearlite, which we call, which is a typical pattern of the Damascus blade. Now, the Damascus blade, the term actually is not, although it's thought to be really to do with Damascus, it's not necessarily that, but it actually it derives from the Arabic term Damashq, which is really this kind of pattern which you see on silk as well, which has this wavy pattern and so on. So anyway, these blades came to be known as Damascus blades. Also, of course, it was exported and such like and sought after. And you can see here this ingot of wood steel. And of course, I won't dwell on this all too much, but we also have the, the 18th century traveler Francis Buchanan observed woods being made by the closed crucible processes. And you're looking at some of the ores here, the banded ferruginous martensite, and these are some of the tuyères and so on. And now I wanted to just point to some of the woods making production sites, which I had studied. One is from Melseravallur in Tamil Nadu. And so here, when you look at the microstructure, if you recall what I showed you in Pattinam, that's typical hypereutectoid wood steel, a globule of hypereutectoid wood steel, which is found in the matrix of this crucible, which I had analyzed during my field work made going back to actually 1990 when I found the site, which is also very important really to undertake field work and document and record these sites because they're all vanishing. And the other aspect is that when you look at the crucible matrix, of course, is silicious, but it also has these rice hull relics, because the process of carburization of the wrought iron was done by packing it with all these carbonaceous materials in a reducing condition. So in a way, there are these parallels which also come to mind when you look at the Zawar process. And another site that I had looked at was material from 3rd century BC site Kodumanal, where you had some of these crucible fragments. And you can see here again, this is a EPMA and electron probe dot map. So you can see the iron-rich areas in this ferrous metal crucible from Kodumanal. And of course, the term ukku also may derive from the old Tamil word urukku, which actually refers to the process of melting. And you also have the Sangam texts of the 3rd century BC to 3rd century AD and so on, where you have the term yegu also coming in, where it also refers to the spears and so on, which are thought to have been made. In fact, there is an account of Zosimus, who is, of course, he's described as an alchemist in the 4th century, the Greek alchemist, who mentions that the Indians used fused iron in crucibles to make weapons, which I think is one of the clearest, at least literary accounts of, observing, the making of crucible steel in India. And of course, there are also these accounts of the iron from which I think is also important because the Romans talked about the iron from the Ceres, and I pointed to you some of these sites such as Kodumanal and so on, which are also, you know, of the Sangam period, and the Sangam rulers included the Cheras, and so the Ceres may well refer to the Cheras of the early historic period. We don't know. Well, finally, I'll just make a couple of points before I wind up, which is that also this ultra-high carbon steel was actually patented by late Professor Oleg Sherby, who's now no more, from Stanford. And he had made these studies, and in fact, I had very nice interaction with him, which I'm reminded of now. And he had undertaken studies in the 80s to show that this was done quite, you know, in an unconnected context. He had studied these ultra-high carbon steels and found that they have the property of superplasticity, which is a high formability at high temperature. And it was only later somebody had pointed out that it is very similar in composition to the Woods Damascus steel, the 1.5% carbon steel. And that's also important in terms of understanding how these blades were forged so extensively, because this property of superplasticity implies that it's highly formable at high temperatures, and that's how they were able to forge these blades also. And also a lot of these skills, of course, have died out. And we had also done some very extensive surveys of the archaeometallurgical debris in the Telangana region, where there's a lot of crucible smelting evidence. And I think prior to Sheffield and all, this was where a lot of the ingots for wood, steel and all that were being made. And amongst my collaborators, of course, were Dr. Jai Kishan, Dr. Jill Joliffe, Professor Ranganathan, and Thelma Lowe had also looked at some of the sites. And just to tell you also that when you talk of the chemistry, so I'm trying to now concentrate on the crucible, which is more the chemistry than the metallurgy. So you find that the crucible as a refractory here has these two layers. There's the inner layer and the outer layer. And the inner layer is more carbon rich or carbonaceous, as you can see by the CT analysis. And if you see, again, this mix of the inorganic and the organic elements, because when you look at that, the fabric of the crucible, so there are a lot of these additions of the rice hull and so on, which actually was very good in terms of improving the refractory properties, because in this case, the rice hull is very carbonaceous, so it was able to, you know, induce this very reducing environment. And yet the outer layer, if you see, that actually has much more of silica. So they were consciously using much more of siliceous materials on the outer layer, because that would then, you know, make it more refractory, so that it wouldn't get, it wouldn't melt down when it was heated at high temperatures and so on. And again, as you can see in that Telangana crucible also, you see these iron droplets and so on, which is a bit similar to what I was talking about from the Male Servalur crucible, and also these coke rice hull relics, which when you analyze it, it has become very siliceous and so on. Well, there's a lot to say about all this, but I think I should really conclude. And a point that I wanted to make also, of course, or maybe repeat the point that Cyril Stanley Smith made in 1980, that the pattern of the Damascus blade was also one of the first specimens to have been studied under the microscope due to the macroscopic structure. And here, I mean, again, it is an etching technology really, because I mean, in the modern day, when we etch this type of steel, maybe in nitol or whatever, then you get the, you know, the pattern, the pearlite and cementite. But so they had this knowledge of etching and so on, and there's a lot to be done there. And this is also, in fact, a blade of Tipu's time, which was, some of them also have the blacksmith's name like Asadullah, and this is another very well-known blade of Tipu Sultan's time, which shows this Koftgari work. And you're also looking at one of the paintings of the Nizam of Hyderabad. And I think this is, yes, this is my one of my last slides. Okay. Yeah, so this is my last two slides really. So I just wanted to point out, I won't dwell on this too much, except to say that you know, the Mushet, who, it was actually Mushet who took out the patent for the crucible steel. And so there was a whole, what is also interesting, of course, about 19th century metallurgy, that there was a lot of the modern science that we know also came about in the way they were trying to understand and study all of these materials. And Michael Faraday, who is the famous, you know, scientist and inventor of electricity, also actually did a lot of studies to understand, you know, the properties of wood steel, and out of that came the field of alloy steels. And even Briand did some astonishing 300 experiments to try and understand, because initially they didn't know that it was actually carbon which contributed to the alloying, which was the alloying element, and that was really through the findings of Tauber and Bergman. Well, I'll conclude with this slide also because I was reminded because of so many of you from the scientific community, and my early inspiration was also through some of my interactions with Professor C.V. Seshadri, who was also, he went from a biochemistry, biotechnology background into algal technology and looking at traditional technologies. And so one of the important points that he had made, and coming now to the traditional knowledge and the skills of the blacksmiths and the, the master craftsmen who are still surviving, and Ashutosh also made that point, and I want to come back to that, we really also need to find a way to engage and draw them into the pedagogy, because as Professor C.V. Seshadri had pointed out, the paradigms of modern science in a way designated many of these technologies as inefficient because of the fact that they are, at ambient temperatures, they take a long time, they're labor intensive and so on. So they're called inefficient. They became marginalized even in the way we talk about technology and its efficiencies and so on. So we need to actually give some value addition also to these crafts and so on, so that we can, better integrate them and give them also better prospects for livelihood and so on. So thank you very much. And sorry if I've gone too much over time.
Okay, yeah, thank you.
So now I stop the share. Yeah.
Yes, yeah, please. So, so I'm taking over the charge. Deeksha had to leave for something quickly.
Yeah.
So there are several questions, but in the interest of time, so I will ask one question. So, what is the composition of the steel, wood steel? And then the other question is, what is the reason for resistance to rusting by iron? So these are the two questions, if you may want to ask.
Yeah. So the composition of wood steel, I think I mentioned it during the talk, which is basically that it's an ultra high carbon steel with about 1 to 1.5% carbon. And as I was mentioning, the wrought iron has less than about 0.04% carbon. So it's not, it doesn't have the same properties of of hardness and so on. Mild steel, as we call it now, has about 0.4% carbon, but this goes into a higher grade of carbon. And obviously it had a very high cutting edge and things like that, for which it was so sought after and such like. And if you read my book on India's legendary wood steel, which also talked about, I mean, there is a very well-known account of how in the Crusades between the King Richard of England and the Sultan Saladin, who had of Egypt, or Salahuddin as you call it, he had a sword of Damascus steel, and he's supposed to have cut, sliced a handkerchief. And in fact, the Sir Walter Scott has written about it in his book, The Talisman, and so on. So there's a lot of, maybe early accounts and so on of such kind as well, which talk about all this. What was the other question now?
So other question is, why the iron doesn't rust?
Yeah, the iron doesn't rust. So I mean, I think that's still there are a lot of reasons which are put forth over there. Of course, Delhi has very low relative humidity, and some studies have been done which suggest that because of the iron was also a very high purity, which was also one of the factors. Of course, it was also partly due to the primitive smelting process that it incorporated a lot of phosphorus, because they were not consciously using fluxes and things like that in the same way that, when you move into the blast furnace technology at much higher temperatures and so on, you need that. So perhaps the phosphorus that was getting in was, and the slag distribution when the forging, all of that also contributed to forming this passive protective film. And some scholars like Balasubramaniam have written on that. And I think that there still is a lot of further work and so on. But mind you, when I showed you that photograph, I don't know what's going to happen with the corrosion now. I mean, with the pollution now in Delhi, because I've seen, I saw around that spot where there is where a cannonball is hitting, there is some corrosion going on there. It's quite rusted there. So we really need to also think about, the future, how to develop the materials and so on to also prevent further corrosion and preservation. That's also very important. And so there is, I think, a lot of interesting work still to be done on that.
Yeah. Thanks a lot, Professor. So it was really wonderful. So in the interest of, there are questions. So
Yes, I can well imagine. So thank you for giving me so much time. I'm sorry if I short over, but and it's a
No, it's
wonderful
fine.
seminar.
Wonderful.
And thank you all, and I look forward to keeping in touch with all of you. So
Yeah, thank